All right, we're just going to take a look at two more quick things, just some other info type of stuff. The first is the leveling effect. And so what we're going to say here is that amphiprotic solvents limit the acid slash base strengths. So let's take a look at some of this stuff. And so let's say you really wanted to protonate something. You want to toss some strong acid in there, right? And so you're going to add some sulfuric acid, some very strong acid that has a pKa of -9, right? -9. And then you want to protonate this B, right? Whatever this B is, you want to protonate it. And so you did some calculations and you decided that a pKa of -9 is good enough to deprotonate it. But then you choose to do it in a solvent of water, right? A solvent of water. Well, then the question is, what's going to happen? Is this base going to deprotonate the hydrogen? Or is water going to interfere and deprotonate it instead? And well, since water is the solvent, it's the major component, right? So the water is actually going to deprotonate the sulfuric acid. And so what you'll end up with H2SO4 minus plus H3O plus B, right? And then if you look at the pKa of H3O plus, it's -1.7. And so while sulfuric acid may have been strong enough to protonate your target B, H3O plus may or may not be strong enough to target your protein or your B, right? So whether you'll protonate B or not depends on the exact strength. But you can see, even though you put a acid that has a pKa of -9, you're limited by your solvent, and your actual kind of acid strength here is a pKa of -1.7. And same thing happens for basic solutions as well with water. So if you put some kind of strong base in, it may interact with the water instead. So you're limited by the acid-base strengths of water if you're using water as a solvent. So water, right, you can think of a pKa of H3O plus as -1.7 or H2O as this 15.7. Cool. And so this is why one of the many reasons, there's other reasons as well, that you'll see water is not often a solvent in organic chemistry. Next up is the solvating effect. And this helps us explain some tiny differences in pKa's. And so this only occurs in a polar solvent. So let's take a look at two compounds that are very similar. So we have this negative charge on this oxygen, and then we have a negative charge on this oxygen, right? The only thing that's different is how many carbons we have attached. And so remember, if this is in a polar solvent, we're going to have polar molecules with their dipoles all around, right? So we have some dipole molecules, and they'll arrange like this to maximize these positive negative attractions. Well, if you think about it, you've got all this bulky stuff right here, that's going to prevent too many molecules from surrounding it. Whereas on this side over here, there's not as many bulky components. And so we'll get more solvent molecules to be able to surround this. And since this is a positive interaction, right, this positive negative interaction helps stabilize things, this one over here is going to be more stable. If it's more stable, it's going to be the weaker base. And then if you think about vice versa, their conjugate acids, this guy over here will then be the stronger acid. So just some other things that you want to keep in mind. This idea of having these bulky groups or less bulky groups, we'll touch back on that in other sections. You'll see it does have a big effect on the reactivity and property of molecules.